Hello, everybody. My name is Xunfei Wang. I'm a professor at KTH, Royal Institute of Technology, Sweden. It's my great pleasure to present our product named as Machine Learning for Power Electronics-based Power Systems, a unified platform for power electronics, power systems, and data science. This project is funded by Digital Futures and C3.ai DTI. The project is in collaboration with Princeton University, USA. Our product team is composed by 5 professors, which include also Professor Lars Nordstrom at KTH, Professor Mingjie Chen, Professor Pratik Mittal, and Professor Vincent Paul, all from Princeton University. First, let's look at what is power electronics. It is a technology that enables efficient conversion of electric power by using power semiconductor devices. These devices are switched on and off by digital computer, which gives full controllability of electric power with wide timescale dynamics. If we look at our power systems today, there are numerous applications of power electronic converters in different sectors, ranging from the renewable power generation, energy storage systems, electric vehicles, to the different types of end user applications like the power to hydrogen electrolyzer, automation, robotics, and motor drives, and other applications. Different from the synchronous generators, the dynamics of power electronic converter are mainly dependent on the digital algorithms used with the digital computer. So the system dynamics in the future power grid will be less physics governed, but more control dependent. So there is a paradigm shift of power systems from the conventional synchronous generator dominated power system to a power electronic based power system. There are several challenges with the dynamics analysis of such power system. The first one is the millions of decentralized power converters complicate the numerical modeling of the future power grid. It is extremely time-consuming and computationally intensive to build the physics-based model of each converter in a large-scale system. The second challenge is the dynamic interactions of those power converters tend to introduce oscillations in a wide frequency range. This is mainly due to the wide time scale control dynamics of the power converters. The last but not least is the vendors of those power electronic converters would not like to share the control algorithms to the system operators. Consequently, we have more and more black box dynamic systems introduced in the power grid. How to handle those black box dynamic systems and how to look at their dynamic interactions is a fundamental challenge. To address this challenge, a common practice in industry is to use the impedance-based method. The basic idea of this method is to do the terminal behavioral modeling of power converter by using the transfer functions. Those transfer functions can be obtained through the measurements of the voltage and current at the terminal of the power converters, and then interpreted as an impedance term in physics. Once we get the impedance information from each converter, then we can perform the system level dynamic analysis by using the frequency domain analysis tools. A problem with this impedance-based method is that the impedance model for each converter is obtained for a given operating condition. Then when we perform the system level stability analysis, the result will be only valid for that specific operating condition. If we want to cover all the operating conditions of the power grid, we have to repeat the whole impedance measurement and impedance-based analysis cycle. This can be very time-consuming in a practical power system. For example, for a wind farm, there are typically 30,000 operating conditions. Let's say if the time need for one impedance measurement and analysis cycle is 10 minutes. Then if we want to cover all the 30,000 operating conditions, then the time needed will be more than 200 days to finalize the overall stability assessment. This is mainly due to the lack of intelligence. We have to simply repeat the stability assessment flow and to cover all possible operating conditions. To address this issue, we come with this machine learning-based approach in this project. The general idea is instead of repeating the stability assessment for all possible operating conditions, can we just do the stability assessment for a small portion of the operating conditions? Then we can use those assessments to generate the data set, which can then be used to train a neural network with machine learning algorithms to get a stability prediction model. Then we can use this stability prediction model to directly predict the system stability for the rest 29,000 cases, for example. In this approach, if we look at the time consumed, we can see there is a big reduction from the conventional approach. Let's look at the general idea for the machine learning-based impedance estimation. We need to first select a set of operating points. For those operating points, we need to generate the impedance dataset, which can then be separated into two parts. The first part is used to train the neural network, and the second part is to test the predicted output of the neural network. In this product, we adopt a feed-forward neural network for the system modeling and stability analysis. And in this feed-forward neural network, we have 3 hidden layers and 25 neurons. Those numbers are chosen based on the specific control of the power converters and analytical model of the converter. Yeah, if we look at the implementation details to generate the impedance data set, there are basically 2 ways. One is to obtain the impedance data by performing the impedance measurement, either in experiments or in numerical simulations. And the second way is to obtain the impedance data set is to just obtain the data generated from the analytical model. Once we get the impedance data set, we need to randomly shuffle the data before we let them go through the training process. And also we need to separate the data set into 3 parts. The first part is the training side, which will be used to train the neural network. The second part is the validation side. This will be used to optimize the hyperparameters used by the neural network. And the third part is the test set, which is used to evaluate the performance of the neural network model. And let's look at the verification result. In this study, we intentionally compare 2 neural network models. The first one is based on the simulation data set, and the second one is based on the calculated data from the analytical model. And if we look at the top figures, the comparison between the neural network models and the test set, we can see the simulation data-based neural network has better accuracy than the other. And if we look at the bottom diagrams, which shows the error histogram with the absolute error and the relative error, we can see a clear difference between the 2 neural network models. So basically, we can say the data generated from the simulation model can give a better prediction for a given neural network trained with the machine learning algorithm. Yeah, let's conclude the product. In this product, we already developed a machine learning framework for impedance estimation of power electronic converter. And based on our study, we can first use the analytical model to pre-train the neural network. And then we can use the data generated from the simulations or field measurements to refine the pre-trained neural network model. The next step in this product is to move forward from the single converter system to multi-converter system. And in this way, we can estimate the network admittance with multiple power converters. That's all for my presentation. Thank you for listening.